change the perspective. I will give you the perspective of a materials producer and with a focus on plastic materials. So I'm working for Evonik. And Evonik is a quite large company with the numbers you can see here. We are today divided in 3 segments: nutrition and care, resource efficiency, where I belong to, and performance materials. The Marl site where I come from is located in Germany, in North Rhine-Westphalia. It's around 2 times 3 kilometers large. We have our own arbor, we have 3 power plants. We have 1,200 kilometers of pipes connecting the different plants at the site. So it's one of the larger chemical production sites in Europe. The materials we are focused on are the ones which are shown here in a magenta color. So our biggest product is a polyamide 12, a special polyamide. But also other materials like a polyamide 1010, 612, a transparent polyamide. So we are more located with our materials in the top of the pyramid of materials. Now I come to additive manufacturing, and I would like to start with some words about the hype, because 3D printing is a word that everybody uses, but I'm really sure what is meant with this. Historically, 3D printing changed its meaning several times. It started with a process invented by the MIT, which used powder, which was glued together with a binder that was printed onto the powder, each layer, and it was commercialized, for example, by the company Z Corporation, which today belongs to 3D Systems. So it was 3D printing at that time, and for the next 15 years was the name for a certain technology and nothing else. Then in the maybe around in the year 2000 or a little bit later, there came up office-friendly processes independent on the technology, and 3D printing was taken for these technologies. And today, in the hype, it can be everything. It can be one of the older meanings. If we use it, it can be the so-called Faber segment, where you have a cheap machine at home. But it also can be used for additive manufacturing. On the other hand, this is a little bit dangerous, because the requirements from the users, from the industrial users or users at home, are very different. So it's really worth to think about, what do I mean with 3D printing now? To be clear, I would like to talk about additive manufacturing, so for serious production using these layer-wise technologies. Why do companies use additive manufacturing or start to think about using it? That can have several reasons. At the end, it's always to save money, to make better products, to make your customer happier than today. But we can drill it down to 3 different areas. The first one is that I simply replace an injection molding part by a part that is produced by additive manufacturing. That's shown on the first picture here. But of course, a part that is designed for injection molding, maybe it's not the best option simply to replace it by an additive manufacturing parts. That's usually only attractive if the number of parts compared to the tool that I would need for injection molding is very small. And that's shown in the picture. So we look at the cost per part here, and only for large numbers Injection molding is the better choice, and for a smaller number of parts, the additive manufacturing version. Let's come to the picture in the middle that shows us new design option. Here's shown at a very artificial part, but which cannot be produced by conventional production methods. Of course, there is much more behind, because companies also can combine in a technical way assembly. So coming from 20 and more parts, integrating all the geometry, all the functionality needed into one part, and this is more complicated, it is more complex, but it can be produced with additive manufacturing. And here we do not have a simple replacement with the same shape of the part, we have a completely new design, and that really make large savings possible. And like we saw in the previous presentation already, we are here not talking about savings at around 5 or 10%, which is a quite common goal. We are talking about savings that can be 50% or more if we do a new design. And last but not least, the right picture here is about customization. So for the first time we have an opportunity to produce batches with a lot one. So each part can be individual from another one. Examples of already commercialized things in this area are the hearing aid shells. Each inner ear is different from person to person, and that is done today with additive manufacturing methods. Let's have a very short look at the industries who are the drivers of this change. It's aerospace. Aerospace had been a front runner using additive manufacturing in the past. Automotive is using it today mainly still for prototyping because they have higher numbers of parts, but there is also a change visible, so more and more companies really find out areas where they can use additive manufacturing. Industrial, healthcare and consumer, we have seen many examples in the past, famous examples where the technology is already used. I would like to come to the polymer-based technologies for additive manufacturing. And this is a collection. Of course, it's not complete. It never can be complete because many companies are working on new technologies which are not yet commercialized, but here are the most prominent ones. So we are a big powder producer, so for us all technologies which use and require polymer powder are for us the most important ones. But for today, I think the powder-based technologies also have the highest potential to come into serious production, simply because you can avoid the support structures with respect to other technologies, and you can build several layers of parts to make a full bucket of parts, which again helps on the economical side. Evonik is famous or well known for the powder we supply to all this SLS technologies, so SLS related technologies, also to newer technologies like for high-speed sintering or multi-jet fusion, and that's where we are well known for. But also for all the powder-based processes, we have a lot of additives in our portfolio, like flowing agents, the aerosol, and other interesting stuff. For FDM, for the SLA or clip technology, as well as for the 3D printing, which means binder jetting here, We have a lot of base materials available as well as additives. Actually, we are in all of the technologies that are in the market today with some ingredient, which is sometimes it's a magic ingredient, which helps to make the process happen. Yes, within Evonik we have many different areas, like I explained before. We will bundle our technologies, our activities, and in an additive manufacturing innovation growth field. And that is quite new. One big column of this activity still is everything that is powder. I already talked about this, and I would like to come to the column in the middle, which explains activities that are more directed into the future. This is our daughter company Creavis, as well as our R&D hub that we have in Singapore here. Colleagues of mine are already also attending this meeting, and I would be happy to introduce them later to you. Within this area we work on new processes or modified processes using synergies between liquid and powder polymer systems. I'm very happy to see this activity, which is the core know-how that a chemical company can bring into this business. Last but not least, the column on the right side describes some metal-based 3D printing, but not as somebody who contributes to the value chain. This is more the user's perspective. So we use metal-based 3D printing to optimize reactor designs, etc. One very important thing, if to be successful in this market, are collaborations and partnerships. I would like to mention Voxeljet, EOS and HP, but there are also a lot of other companies like Evolve in the US. We founded the DMRC, which is an institute for additive manufacturing for industrial applications in Germany and Paderborn. So it's very important. You need the know-how of all partners to really be able to make a good solution for the end customer. Let me come to powder. If you are looking for a powder, normally the first thing that is discussed are mechanical properties, is the surface quality, and I added the processability, and that means the processability in an additive manufacturing machine. You will not find anything about that in a data sheet, but it is one of the most important properties that a powder can have. Because if you don't have a safe processability of powders in the machine, then it's good for prototyping, but not for manufacturing. For manufacturing, you need a good reproducibility and reliability. And that's why I would like to strengthen the processability here. Let's have a look into the Polymer 12 powder, which is in the market today. We have mainly spherical particles. We call it potato-shaped particles. We have a very narrow grain size distribution. The medium grain size is about 55 micron, which is the thickness of a hair approximately, and plus minus 20 micron for D90 and D10. The material has a special high crystallinity that's due to its production process, but it helps in the laser sintering and other powder bed fusion processes a lot. We need a good melt flow without shear. In contrast to injection molding, we do not have any shear, in additive manufacturing processes, but at the end we would like to have a completely dense structure. And of course, surface properties can be tailor-made to any application. And we adjust all these material parameters. If you look at the production chain, starting from the crude oil, in this case, coming to the monomer, the polymer, the powder, and powder modifications which are necessary. And then at the very end, we use the material in powder bed fusion machines for quality checks, for example. But in each of these steps, a certain property of the powder is fixed. And it's really essential for us that we have access to the complete production chain. If you only have the chance to start with a powder modification and all the other parameters in the steps before are not set properly, then you are lost. Then you will probably not come to a really good powder. And if I look at the whole chain again, but with a different perspective here, we added also application testing, polymer testing, a standard committee, analytics. That's all necessary, or work in these steps is necessary if you have a really good powder and want to get it into the market. An example for materials properties, I already mentioned the polyamide 12. The properties of a polyamide 12 grade are shown here. They are very comparable to injection molded polyamide 12 parts with a comparable grade. You see the higher crystallinity here again, which shows that I have a higher modulus of elasticity than in a normal injection molded polyamide 12 grade. An elongation at break of 15% should be good enough for most of the design topics. And I compare this material today to a new material. It's a polyether blockamide, Vesicin 3D 3054, which is a rubber-like material, but not a TPU. It's a PIBA with slightly different properties. You see it's much softer than the standard polyamide 12 grade, and of course this opens new applications for additive manufacturing if such a material is available. For example, printing sealants, tubes and hoses that have to be flexible. Another example is a material. It's a polyamide 613, which already is not in the market, but it competes or can compete to a polyamide 6. It has a much lower water uptake. We have an elevated temperature resistance because the melting point of the material is at around 212 degrees, which makes it possible to use existing machines in the market and to be able to work with this material. And we have improved impact strength and an improved stiffness at the same time in one material compared to polyamide 12. Normally you can improve one of these properties and pay the bill on the other side, but here both properties can be improved at the same time. Again, some of the technical information about this material. You see it behaves a little bit as if it was filled, but with really extremely good mechanical properties. Last but not least, taking a deeper look in development, or in development which is nearly finished. This is if you need filled materials. Today it's state of the art to have a dry blend between the polymer particles and the filler particles. and that leads every time that you transport the material, that you move the material into the machine, for example, you will have a slight separation because the particles have a different density. That can be avoided by using a new method to produce powder. So we are able today to coat the filler particles with our Polymer 12, and so we can offer a kind of composite material today, avoiding all these disadvantages I mentioned. Let me say a word about quality. In the very beginning I mentioned that the different segments of the market have very different requirements. I can say quality is a requirement that's needed everywhere, but of course for production purposes it's a special topic because we need this reproducibility and reliability of the process. You have seen the whole production chain that we have from the crude oil on, and in each of the single steps we do our quality assurance. We have approvals, ISO approvals for quality, and it's for us a very important topic because I think we do not lack only new materials. There is also a need of reliable materials in the market. I promised to talk also about the hurdles we see to make additive manufacturing really happen. The green part in the middle is the process for laser sintering, for example, but it can be something else, where you need a machine and a material. And it seems that we know everything about this process and control it. But all the processes that are needed before that and after that, what happens in the machine, have to be automated and described. And the best thing would be if there would be a software also covering all these different steps. But that is something that is missing today. We only look in most cases at the green part, at the process, but that's far too less. And I have to admit, for each single application, these pre- and post-processing steps are very different. Sometimes it's a kind of post-processing because a part has to look very nice, it has to have a very smooth surface. In other cases, it has to be glued together with other parts. It can be very different. So it has to be worked on for each single application. There will not be one big application that suddenly starts with additive manufacturing, but we have to work in many companies at the same time in parallel to get different applications started. And that's exciting. I think we are in the middle of the process. And let me finish with another example. We have designers and artists seen in the past as early adopters of new technologies. An example here from the 19th century, where the welding of wood had been invented. And from this point of time on, the designer started to create, in this case, a completely new chair. Then we had injection molding coming in. It's also not a very old technology. So it's from the mid of the previous 100 years. And here again, the designers start to use their new possibilities to make the Pantone chair, which is quite famous, for example. And last but not least, what we saw today in the past years, it's really that designers try to figure out the limits of the new technology as well. You see on the left upper side a chair. The chair is hollow in the middle, and of course no laser sintering machine is large enough to produce it. So there is a kind of modular system where it's stacked together. But also lamps, shoes, or the small chair on the right side are really exciting examples how designers show us what in principle is possible with the technology. I think now it's part of each single company to check with the existing things and the developments for the near future what they can do and how they can use additive manufacturing. And we will be very happy to be a partner with our materials. Thank you very much.